Hi guys, I'm Nancy, and I'm going to show you how to find the limit at infinity, or negative infinity. Limits are a pretty big topic, kind of a mess, so I have a few videos. If you're actually looking for limits not at infinity, but at a number, or an introduction to limits, what they mean, you can use the links in the description to jump to those explanations. But if you are looking for limits at infinity or negative infinity, here are the types I'm going to show you. Okay, so here are the kinds I'm going to show you. If you see the kind that you're working on already, you can skip ahead. Just check the description for a time to skip to. But I'm going to show you if you have a polynomial, like an x expression in your limit, or a constant, just a number, both as x goes to positive infinity and to negative infinity. This is a quick type I'm going to show you. The most common type is rational expressions in your limit, something in the form of a fraction. And there is a shortcut for this type based on the degree of the numerator and the degree of the denominator. What is the degree? It just means the highest power that appears. So you can use a shortcut to find the limit by comparing the degree of the top and the degree of the bottom in your rational expression. I will also show you the formal algebraic way of finding it, but this is a really useful shortcut. Then we'll look at if you have something like sin x over x in your limit as x goes to infinity or negative infinity. And then we'll look at if you have an exponential type. So the limit as x goes to infinity of e to some negative variable exponent. So let's look at the first type if you have a polynomial or constant in your limit. Okay, let's look at this type really quickly. If you have a polynomial, an x expression, or a constant, just a number in your limit as x approaches infinity. Say you have something like the limit of 2x as x approaches infinity. How can you figure that out? Basically, you need to figure out what happens to 2x as x goes to infinity. As x becomes huge, as x becomes very large, what is happening to 2x? Well, anything like 2x, x squared, x cubed, powers of x, they vary directly with x, meaning if x gets big, then they also grow in the same direction. So this will also become huge, very, very large. You can think of it as plugging in infinity for x. That's not technically what's happening here, but I think it's helpful to think of that. If you put in infinity, or some huge number for x, what would 2x be? It would also be some huge number, and we still represent that by infinity. So we put infinity for the limit. Then think about what would happen if x approached negative infinity. Well, if you put in some huge negative number for x, 2x would also be some huge negative number, and it's only getting more and more negative, becoming larger and larger in the negative direction. So this would also be huge and negative, and we would write negative infinity for the limit. Now I should quickly point out, I put equals infinity and equals negative infinity. It does not actually equal infinity. You can never reach infinity or negative infinity, but in limit language or limit speak, we write that it equals infinity or equals negative infinity because it's heading in that direction. That's what it's approaching as x goes to infinity or negative infinity. So let's look at another polynomial that's a little larger. Okay, so what if you have a larger polynomial x expression, something that starts with x squared as a leading term? Well, basically, for really large x, you don't have to worry about any lower degree terms. You only need to focus on the leading term. So you can actually just kind of ignore any other terms and focus on that. So what happens when x becomes extremely large? X squared also becomes extremely large. They grow in the same direction. So this would be equal to infinity. The limit is equal to infinity. If x instead approached negative infinity of x squared plus 2x plus 5, again, we don't care about the lower degree terms because when x is extremely large, none of those lower terms are growing anywhere near as quickly as the first leading term. So they don't make a difference overall. It's really just the highest power term that appears that counts when finding the limits. So anyway, it's x squared that you care about in this expression. And if x became extremely negative, very large and negative, squaring it would make it positive again. No matter what number that was, it would become positive. So again, you can think of it in terms of plugging in negative infinity. You can't really plug in negative infinity, but it's helpful. Putting in a negative infinity and squaring it makes it positive, a positive huge number. So we put, again, equals infinity. You might be wondering, what if the leading term isn't positive? That's a great question. So if you instead had, this, limit as x goes to positive infinity of negative x squared plus 2x plus 5. These lower terms don't affect your limit, but this one does. Negative x squared means x is squared first and then the sign is changed, becomes negative. So if you put in a huge number, infinity, squared it, it's still positive and huge, positive infinity, but then you flip the sign after, so it actually becomes negative infinity. This is why I think it's helpful to think of plugging in infinity and negative infinity, although that's not really algebraically what's happening, but it's helpful. And then use what you know about even powers and odd powers to find these limits. Like if you are given this one, the limit of x cubed as x approaches infinity, this would also be positive infinity. But if you had the limit as x approaches negative infinity of x cubed, just remember that for odd powers of x, a negative number raised to an odd power is still negative. So that's true if it's x to the 5th, 7th, x to the 3rd. So this would actually be negative and large, so negative infinity. Hopefully you're getting the idea. If it were x to the 4th here, it wouldn't matter if we put in negative infinity. What would come out would be large and positive, so it would be positive infinity. And then this sign here does matter if there's a sign out front. You know, even if it were negative 2x squared, if there's some number, overall it would still be negative. One last thing I want to show you before we move on to the real meat of limits at infinity, which are the rational ones. If you ever get a constant, like your function was just a number, a constant, like this, limit of 3 as x approaches infinity, there is no variable, there's no x that appears there, so no matter what happens to x, it doesn't affect your number, your constant. It's a constant. It stays the same. So your limit would actually be just that constant, 3, whatever number you had. Same thing here. It doesn't matter if x is going toward a negative large number. Your function is just 3, so the limit is still 3. It's a horizontal flat line forever. Okay, so now let's take a look at the rational kinds of limits at infinity. Okay, so here is the most common type of limits at infinity, which is rational expressions. The limit of a rational expression, rational just meaning in the form of one polynomial over another polynomial, so a numerator and a denominator, a fraction, if you will. So just remember this is in the form of a numerator over a denominator. So for something that looks like this, a rational expression in your limit as x approaches infinity or negative infinity, there is a really fast way of getting the limit, and it's a shortcut. It's really the fastest way, and I'm going to show that to you first. Basically, all you do is compare the degree of the numerator and the degree of the denominator, the degree of the polynomial on top and the degree of the polynomial on the bottom, to find what the limit should be. And there are 3 cases I want to show you. I will show you the formal algebraic official way of finding the limit of a rational expression for x approaching infinity. But first, I think it's really useful to see this fast way based on these three cases. So let's look at those. Okay, so these are the three main cases for finding the limit with a shortcut for a rational expression as x approaches infinity or negative infinity. Basically, all you need to do is compare the degrees of the numerator and the denominator. The degree is the highest power that appears in a polynomial, so the degree of the numerator is the highest power of x that appears in the top, and the degree of the denominator is the highest power of x that appears in the bottom. So in this expression, in this example, the degree of the numerator would be 2 because the highest power of x that appears on top is x squared. The degree is 2. And the degree of the denominator would be 3, since the highest power of x that appears in the bottom is x cubed. Those are the numbers that you're comparing. So because the degree of the numerator, 2, is less than the degree of the denominator, 3, the limit will be 0. The limit will be equal to 0. Basically, because this function is bottom heavy, a higher power on bottom than on top, the rule is that the limit will end up being 0. The reason is that if you just look at the leading terms, the highest power x squared and the highest power on bottom x cubed, the overall form of this expression is 1 over x. This would simplify to 1 over x. It's the overall form of it. And if x became very, very large, infinity, 1 over infinity, or 1 over a very large number, is basically 0, is the limit. The value is approaching 0, so the limit is 0 in that case. This is true even when x is approaching negative infinity. So this is true if x is approaching positive infinity, which you just saw, or negative infinity, because even if you put in a huge negative number here for x, 1 over a huge negative number is approaching 0. It's just approaching 0 from the other side. So this rule, this case will still hold. It will be equal to 0. Okay, so let's look at the second case. Look at this limit here. If the degree of the numerator is the same as the degree of the denominator, so in this example, the degree on top is 2 from the x squared, the degree on bottom is also 2 from x squared. If they are equal, then to find the limit, the fastest way is to take the ratio of the leading coefficients. So write the fraction or the ratio that is the leading constants out front of the highest power terms. Okay, so let's look at an example. For the sake of the example, let's pretend that you're doing the limit as x approaches negative infinity, and then we'll go back and look at the other one. The limit as x approaches negative infinity of this expression, you can just, because the degrees are equal, because it's balanced in that way, you can just focus on the leading terms. So here that's 2x squared and 8x squared. And the reason for that is that when x is extremely large in the positive or negative direction, these lower degree terms don't affect the overall limit value in the end, so you can ignore them. Just focus on the leading highest power terms. Anyway, now you have the limit as x approaches negative infinity of 2x squared over 8x squared, and you can simplify this with algebra. Those x squareds cancel. We have 2 over 8, which of course simplifies to 1/4. So your limit of that rational expression is the actual value, actual finite number, 1/4. Notice that because the degrees are balanced, because it's the same x squared on top and bottom, those x squareds drop out. They disappear, they cancel. This would be true even if you had x cubed and x cubed, x and x, etc., etc. So because of that, it never mattered that x was approaching negative infinity instead of positive infinity. We only cared about the ratio of those leading constants, those leading numbers out front. If this had just been x squared, there is a 1 there. Remember, there would have been a 1 as your leading coefficient. But we had 2 and 8, and that simplified to 1/4. So as a rule, as a shortcut, no matter if x is approaching positive or negative infinity, when the degrees are equal, you can just write a ratio, a fraction of the leading terms, and it becomes just the leading constants, the leading coefficients that matter to find your limit value. Okay, so the last case, what if the degree of your numerator is greater than the degree in the denominator? So in this example, x squared has a degree of 2, x has a degree of 1. So since 2 is larger than 1, what do? Well, your limit will either be positive infinity or negative infinity, depending on your leading terms. So say that you wanted to find the limits as x approaches positive infinity of this expression. You only need to consider the leading terms. So we can write the limit as x approaches infinity of 3x squared over x, and then you'll need to use algebra to simplify and get it down to the simplest x expression that you can. Okay, so as you can see, simplifying this expression gives you the limit of 3x as x approaches infinity, and as you know from earlier examples, as x approaches infinity, something like 3x would also approach positive infinity. So in that case, your limit was positive infinity. If instead all along it had been as x approaches negative infinity, in the end, using your 3x simplified expression, if x approached negative infinity, this would also approach negative infinity. So that could happen as well. So as a rule, you'll just need to use the leading terms, write the ratio, and take the limit of whatever simplified x expression you get in the end. So I would say it could be infinity or negative infinity, depending on your rational expression. Okay, so those are the three main cases for finding the limit with a shortcut. Now let me show you the formal algebraic official way of finding the limit of a rational expression really quickly, just so you see where this all came from. Okay, so let me show you really quickly why that shortcut works, and I'll use that first case where the power on top was lower than the power on the bottom. Basically, the algebraic, formal, official way of finding the limit of a rational expression is to use algebra, and basically you divide every term that appears, every term, by the highest power of x that appears in the denominator. So the highest power that appears in the denominator is x cubed. So you can find a value for your limits, an actual number, by dividing all of these terms by x cubed. So here I've divided every term by x cubed, and this of course can simplify. Each term within this expression can simplify. All right, and then the magic of that is that now if you look at each term individually, if you think of x getting extremely large, if you think of putting a number like infinity in for x, anything with an x in the denominator would go to 0, because any number, any finite constant number that you know over something like infinity is essentially 0. So for large values of x, each of these little terms gets arbitrarily close to 0, super close to 0, and you can, for all purposes for the limit, zero them out. See, anything with an x power in the bottom and just a number on top goes to 0. We have this 2 left in the denominator. So this simplifies to 0 on top, because we had 0 plus 0 plus 0, and a 2 on the bottom, which of course is just 0. So I showed you this way, this technique for that first case, but you could do this for even the cases where the powers are equal, where the degrees are equal, where the degree is higher on top than on bottom. And in each case, you would find basically the end that we found in the shortcut case. But of course, you can tell that this is a longer method. So it's faster to use the shortcut, but it's good to see this. It's good to see where it comes from. All right, I also want to show you one more thing that's useful that comes up a lot. This confuses people sometimes when they just see 1 over x. It is technically rational. That's why I'm putting it in this section. But the limit as x approaches infinity of 1 over x is 0. Because if this x in the bottom is getting extremely large, this small 1 over an extremely large number is tending towards 0. It's practically 0. So in the limit, the value is approaching 0. And the same is true even if x is approaching negative infinity. That also equals 0, because even if it's 1 over an extremely large negative number, it is heading towards 0 just from the negative direction. It's 1 over a very large negative number is practically 0. Be something like negative 0.000001, small and negative, but practically 0 in the limit. Okay, in that vein, what if you had 1 over x squared? If you have 1 over x squared, again, even if it's x squared down in the denominator, 1 over infinity squared is still practically 1 over infinity, which is extremely small and is 0. So I think you're seeing a theme here. Even if it's negative, the negative gets squared and becomes positive, but it's still 0, 1 over a very large number. So in general, if you have 1 over x squared, 1 over x cubed, no matter if x is approaching positive infinity or negative infinity, it's going to be equal to 0. It's going to be 0 as long as n is a positive power, like 2, 3, 4, etc. So 1 over some huge number is going towards 0 in the limit. All right, let's now look at a type where you have sin x over x in your limit. Okay, so here's a third common type of limits at infinity, which is if you have the form sin x over x or something like that as x approaches infinity or as x approaches negative infinity. There's a property that you can use if this comes up, and that property is that the limit of sin x over x as x approaches infinity or negative infinity will be equal to 0. And you can use that even for forms that don't exactly look like that. Before I show you these examples, be careful. This looks a lot like another property that comes up in limits at a finite value at a constant value, and I have a video for that, but don't confuse it with the other one, which is this. So warning, not to be confused with this other one. But if you do have the kind that's limit as x approaches infinity or negative infinity of sin x over x, it will equal 0. So let's look at this first type. In this case, sine of 3x over x doesn't exactly look like this property. So you can try to make it look like that property. But no matter what you get, it's still going to end up equaling 0. Let me show you what I mean by that. So sine of 3x over x, in order to use this property, you need to have sine of something over that same something, and then you can set it equal to 0. So right now we have sine of 3x over x, not 3, so we can write the 3 in. but because we put a 3 down here, you'll also need to put a 3 on top. You can write it as 3 over 1. But the beauty of this is that this whole thing is equal to 0 because the sign of some expression over that same expression is exactly equal to 0. So this equals 0 because 0 times 3 is 0. Anyway, I'm showing you specific examples, but pretty much anytime you have sign of an expression over an expression, it will be equal to 0. So even in this case, you could break this 6x into 3x times 2 so that you have the form you need, and this equals 0 because of the property. But 0 times 1/2 is again 0. So I think you're seeing a pattern. No matter what specific form you're given, if it's the limit as x approaches infinity or negative infinity, if you had same thing, it would still overall equal 0. There are a few other forms that this could appear in. For instance, this form, sine of x squared over x, doesn't matter. If you see that it's sine of x over x, sine of something over something, it will end up being 0. And let me show you why. Because say that you write what you need to use the property. You break this into sine of x squared over x squared, but because you added an x in the denominator, you add an x on top. Well, this part equals 0. And then if you take the limit as x goes to infinity, putting in infinity or a huge number for this x times 0 would still be 0. So I think you get the point. Usually when it looks like this, it will equal 0, but this is the property that you want to use, and it's true for positive infinity and negative infinity. All right, now let's look at the last common type, which is an exponential expression. Okay, here's the last major common type I want to show you, which is exponential. Say you have something of the form e to the negative 2x, the limit as x approaches infinity. You may look at that and have no idea what to do, what strategy you could use to find it. The key here is the negative exponent, the negative power, to use what you know about negative powers to rewrite it with a positive power, and then it will be clear how to find the limit. Okay, so if you remember a negative power, you can use that to rewrite an expression as 1 over the positive version of the power. So instead of e to the negative 2x, we can rewrite it as 1 over e to the positive 2x. Why? This is really useful because now when you look at this form, if you put in infinity, if you think of plugging in infinity, even though we can't technically do that, but it's useful to think of it that way, e to the 2 times infinity power, you can think of rewriting it as 1 over e to the 2 times infinity power. If you think of plugging it in, 2 times infinity is still infinity, so this is really 1 over e to the infinity power. E to the infinity power is still huge and positive, so this is basically infinity for the purposes of our limit. So it's really like you have 1 over infinity. 1 over a huge number tends toward 0 in the limit, so this is equal to 0. All right, one other type I want to show you. What if you had the limit as x approaches negative infinity of e to the 2x power? This is the reverse of what I just showed you. Basically, you can think of putting in negative infinity for x, I think is the fastest way to figure out what the limit will be. So if we think of this as e to the 2 times negative infinity power, that's 2 times negative infinity is still negative infinity, so this is e to the negative infinity power. And a negative power, we can use that to rewrite this as 1 over e to the positive power. So 1 over e to the infinity. E to the infinity is huge, is basically infinity. And this will go toward 0 because 1 over some huge number is 0. So this limit is also equal to 0. So I hope this video helped you figure out how to find the limit at infinity or negative infinity. I know that limits are everyone's favorite topic. It's okay. You don't have to like limits, but you can like my video, so if you did, please click like or subscribe.